Okay, so in this video, we're going to look at Atwood machines, right? Continue talking about Unit 2 dynamics here in AP Physics 1. And so these are often also referred to as connected objects because they're often either touching or connected by a string. And ultimately, you're going to have to probably find the acceleration of a system or acceleration of a certain block or object, and then find the tension or contact force between objects. So one thing to note, Atwood machine is a device where two masses are connected by pulley passing, or excuse me, connected by string passing or pulley. That's this device, and really it's just really to study mechanics. Okay. The pulley in the system is always going to be ideal, meaning it's going to be massless and frictionless, so we don't have to worry about any effective friction at that point. Anything, and same thing with the string. So it's always going to be massless, frictionless string. A modified Atwood machine, which is the one that you see here to the bottom, is one in which one of the masses is going to rest on the table. Or later we can introduce in an inclined plane. So this is still technically a modified Atwood machine because the masses aren't just hanging, right? One's on a table, one's hanging. Now, because of the string in the machine is also ideal, right? The tension is going to be the same. So the tension will be the same in this part, which is that part, okay? And then the same thing throughout. So even though it's a single string, the pulley kind of breaks it up into two pieces, okay? Now, with that being said, also, not only is the tension going to be the same, so is the acceleration of the system is going to be the same. And then the way to make problem solving easy here, right, is to make sure each mass has its own coordinate system. But that coordinate system kind of follows what the pulley does, okay? And so just some problem solving tips when it comes to connected objects, Atwood machines. One, you're always going to divide by total mass. Okay, at some point in time, especially to find the acceleration, okay, you're going to end up dividing by total mass, regardless of which method you use. Okay, now we talk about there's multiple methods here. So my recommendation is to find acceleration, right? Treat it as a single system. Right? You're still going to do draw, sum, solve, but you're going to treat it as a single system because what that does, it takes tension out of the process. And you would just identify what is trying to pull this system, right? What is trying to move the system, okay? Same thing here. I treat this as a full system. So it eliminates the tension, right? And what is trying to pull the system? Now, if there's friction involved, which we'll get into later, okay, that would try to pull it on that side. And then once you have the acceleration of the system, then you can go back and find the tension of the system or the tension or any kind of other forces you're looking at. So let's look at a couple of example problems. So here we have two masses, one of 5 kilograms, one of 2 kilograms, hanging on an Atwood machine. And we're going to determine what is the acceleration of the two masses when released from rest, and then what is the tension in the string. So again, we're going to treat this as a full system. And so the only two things that are trying to move this system, right, are going to be the weights of the two objects. Now, we talked about previously that each system would have its own coordinate, or each object would have its own coordinate system. So in general, I like to put the coordinate system in the direction, or the positive in the direction of the motion. So because M1 is heavier, it's going to move down, and M2 is going to move up. So what that means is that my weight of M1 is going to be my positive direction. My weight of M2 is going to be my negative direction. And now we're going to have the total mass running around in there, right? So there's our draw step. Okay, now we're going to sum the forces. Sorry about that. In the direction, right? So we're going to sum the forces, and we only have if you want to say it, we only have a vertical direction. So we're going to say FG1 minus FG2 equals M total A. And since we're looking for acceleration, we're going to simply divide FG1 minus FG2 over m total, right? And there's our red flag that we're going to always divide by total mass when we're finding acceleration. But we know that Fg is mg, right? And so this is kind of our acceleration of an object, with an Atwood machine. So now I can plug my numbers. So I'm going to say 5 times 9.81 minus 2 times 9.81 divided by 5 plus 2. I'm going to get an acceleration of 4.2 meters per second squared, right? And it's going to be positive because both of them, right, the way I chose my coordinate system. Now, let's look at finding the tension. So now we're going to, let's say we're going to do block 1, right? So M1, the one on the left, the bigger one. So we're going to have FG2 down, tension up. And so, again, my positive for FG1, sorry, I put a 2 there, is down. So it's going to make my weight down. Okay, now I'm not going to divide by total mass because I'm looking at an individual block, right? And so I'm going to do some algebra. I'm going to add T over and subtract the M1 over. So I'm going to get M1 times G minus M1A equals tension. I can factor out an M1. And so my tension is going to be M1, which is 5, times 9.81 minus 4.2. And so the tension in my string is going to be 28 newtons. You could do this for mass 2, but you're going to find that you're going to get 28 newtons also, because it's going to have, the only difference is that minus sign for G minus A will be a plus sign. All right, so let's look at another type of connected object problem when you have multiple boxes pushing on each other. So here we have 3 blocks on a frictionless horizontal surface. A force of 96 newtons is going to push them, right? And then it's going to be pushed at A. Now, if each object has a 10 kilogram mass, what are the acceleration of the system and the force of contact on each block? Okay, so to find the acceleration, we're going to do our single system. So we only have one. Our free body diagram is going to be one force. And so we're going to say force equals M total A. So it's going to be F equals, oh, sorry, let me do my algebra. I'm going to divide. So F divided by M total. It's just going to be 96 newtons divided by 30 kilograms because it tells us that each block is 10 kilograms. So 96 divided by 3 is going to be 3.2 meters per second squared. And now I'm going to start looking at the individual pieces to find the force of contact on each block. So again, so B is going to push on C, C is going to push on B, A is going to push on B, B is going to push back on C. Okay, so I'm going to start with C. It's my easiest one. So the only force I have with C is what is being pushed from B. So F of B on C. Okay, it's the only force I have on C. And so I'm going to say F of B on C equals M of MC times A. And so now I'm going to do is plug in 10 times 3.2. And so that's going to be equal to 32 newtons. Okay, so this is block C. But note that B is pushing on C. Well, guess what? C is pushing on B. So now I'm going to look at B, right? And I could look at A if I want. So I'm going to have, for B, I'm going to have F of A on B and F of C on B. So I'm going to have F of A on B minus F of C on B equals MBA. And so I'm going to add F of C on B over because I'm looking for F of A on B. Right? And so I have F of A on B equals 32 newtons, because that's what I found for part A, plus 10 times 32, or sorry, 3.2. And so the force of A on B is 64 newtons. right? So there are my forces, points of contact, right? So 32 newtons, push back at 32 newtons, 64 newtons, push back on 64 newtons. Okay, so that's it for connected objects. In the next videos, we're going to look at inclined planes.